have been able to actually discover drug candidates that target the genes that have been adapted to an epidemic back in the past, that are actually drugs that are being used currently to treat the current pandemic.
Hey everyone, welcome to SwitchHubTV. It's your host Wei and John. Today on the show we have Dr Yassine Souilmi. Yassine is a postdoc researcher at the Australian Centre for Ancient DNA at the University of Adelaide. He works on both modern and ancient genetics to help better address questions regarding human health. Yassine, welcome to the show. How are you?
Thanks, Wei. Thanks for having me. Thanks, John.
Thanks for being on the show. We want to start off with, how and why did you get into science?
I guess I've always had an interest in science. I've heard stories from both my parents, dating back when I was, 4 years old, and I've always had that interest in things, how they work, and interest in solving problems. And so I carried that interest in problem solving with me throughout my life, on and off, obviously, throughout different phases that sort of took center stage or faded a little bit in the background. But then, once I graduated high school and it was time to make a decision about which career I want to go into, I chose science, despite everybody telling me you're crazy, you either have to pick law or medicine or finances. But I followed my heart, and I'm glad I did.
And so why I guess genetics in particular? Was it something about it that drew you to it?
That's a really good question. Actually, after graduating high school, I had a very, very high interest in physics, and so I started an undergrad degree in physics, which I finished. But by the time I finished it, it wasn't exactly what I wanted, and I wasn't sure exactly what I wanted at that time. And so probably luck, series of good coincidences, I met some of the right people that influenced me, and I decided to do a master's degree in bioinformatics, which is an interdisciplinary field that takes people from physics, math, stats, chemistry, and biology, and computer science. And so, to be honest, I started that degree just as a placeholder, like wait and see. And then I ended up finding that it's actually the thing that I really love. It's sort of at the interface of technology and human health and genetics, all of which are of interest to me. So it was just the right balance field for me to sort of scratch all the itches and all the curiosities that I have.
And what exactly is ancient DNA? Because from my knowledge, DNA can degrade and lose integrity over time. How old can these samples get, and what sort of samples are we talking about? Could we dig into the ice shelves of Antarctica and find DNA that's been lying there for millions of years old and still be something that we could study and look into?
Yeah, that's an excellent question. Ancient DNA is really every bit of DNA that we can extract from something that's dead, whether that's a microorganism or a mammal or a human. The range stretches basically from a few years all the way back. I think the oldest sample that we have been able to get DNA out of is nearly 1 million years old. I think it's a mammoth from permafrost up in the north, in the Arctic Circle. And yes, your question about can you dig in Antarctica and extract DNA from there? That is definitely possible, and people have tried with different degrees of success. Obviously, DNA degrades as it is exposed to external factors. So temperature plays a major role. The warmer it is, the less the less preserved the DNA becomes, and the more fragmented it becomes. And then once it fragments beyond a certain point, yes, we can get it, but we can't extract any meaningful information out of that because it's just too short. And there is definitely a virtual sort of upper age limit to how far back we can go, which is in fact roughly just above 1 million years. And that has to do with how DNA breaks. So DNA breaks and there are different sort of environmental factors. So chemical factors like moisture and all that tend to accelerate that. Temperature, as I said, the warmer it is, the faster DNA breaks. But also DNA, as every other molecule on Earth and in the universe, they break because of the collision of these molecules with cosmic rays. And so if you take the perfect preservation conditions and you put even DNA in a freezer, a -80 freezer, that's the perfect preservation conditions for DNA. After a certain period of time, it's going to start breaking under the influence of cosmic rays that penetrate everything. And so that there is then like a virtual age of about 1 million years, which makes it really hard to get any meaningful DNA from dinosaurs or anything like that.
So Jurassic Park is a no-go. That's what you're telling us.
It's not happening. We can guess what the DNA of certain creatures from the Jurassic might have looked like, but we wouldn't know exactly what it was like.
Right. Okay.
It's hard. Yeah, it's nearly impossible.
Go on, John. Go on.
So how did they come into a conclusion? What would like a T-Rex would look like?
Well, sort of all the. Oh, you mean the current image we have of a T-Rex, or how?
Yes, that's right.
How
you use DNA? Yep.
That has nothing to do with genetics. That is completely based on morphology. So people have found fossilized remains from dinosaurs back in the past, and then they assembled them, and that's how they found the sort of the skeletal shape of T-Rex and a number of other creatures. And then basically there are certain back in the past that was done by hand, but now there are certain computer algorithms that can take sort of a 3D scan of a skull or skeletal material and give you roughly how it might have looked like by trying to reconstruct sort of the muscles and the tissues around that.
I see.
Yeah, because you can roughly guess how much sort of tissue, whether that's fatty or muscular, etc., is formed around a given bone based on the thickness of the bone. Bones get only thick and strong and dense only if they have to support a lot of weight. That's why we had the bones at the femur around our legs are much thicker than around our arms. It's not by design, but it's by necessity.
Yeah, Yassine, I want to switch the topic of the conversation for a bit to focus a bit more on the present, but of course, still based on your line of work, being, I guess, ancient DNA. You and a team of researchers recently published a paper titled "An Ancient Viral Epidemic Involving Host Coronavirus Interacting Genes More Than 20,000 Years Ago in East Asia." So there's a lot to unpack there. Could you start with what the research was about and what exactly did your team discover?
So before I go there, I'd just like to draw a segue or a link from what we were just talking about and go to this. Viruses are really, really tiny creatures, and their DNA is, well, some of them have DNA, some of them have RNA, which is just an alternative molecule to encode genetic information. It's really tiny. And also, like the shell of the virus itself is very small. So they don't have bones that can preserve DNA for a very long time. And beyond, probably few thousand years, it's nearly impossible to find viral DNA preserved in anything. And so what are we left with is actually finding, hopefully, signatures of or markers of the interaction between the host and the virus. So it's sort of that circumstantial evidence of the presence of the virus at a certain time rather than isolating the virus. And that's kind of what motivated the research that we did. It's our inability to look too far and back in the past into the presence of viruses. And that has been done to a certain extent for other viruses or other organisms, but we wanted to drill down on coronaviruses for very obvious reasons. It's an epidemic that's bringing the world to its knees. And every bit of information is very useful. I mean, even if research like this might seem, oh, why are you looking into epidemics that might have happened 20,000 years ago? How's that helping us today? Besides the cool story, it's helping us very, very much because it's highlighting in the absence of medication and the absence of protection and the absence of public health policy and vaccines, how did our ancestors respond? And it also gives us an idea about the scale of a certain of these epidemics and how big and how long they can stretch. And that's what motivated that with the work you're referring to.
Right. And what sort of sample? Yeah, go on, John. Go on.
Yeah, no, go on.
What sort of samples were you looking at in order to get this data? Was it just modern human DNA and sort of combing through the human genome to look for imprints that, like, I guess, ancient or older coronaviruses might have left in our genomes? Is that what it was about?
That is absolutely correct. So we took DNA data from about 2,500 people from around the globe, and we said, okay, we have a set of genes in our bodies that are known and have been already characterized early in the pandemic to interact directly with the virus. And so when the virus invades or infects somebody, the virus' primary function is to create multiple copies of itself inside the host, and then hopefully for the virus, not for us, it jump from one person to the other, and that's why they create multiple copies. And so the way they do it, the virus is actually completely unable to create copies of itself. And to be able to do that, the virus needs to actually hijack the human cell's machinery to create copies of itself. And the way it does that, it's actually very interesting. It's got a series of genes of its own that activates certain human genes that turns on the functions that the virus wants and needs to multiply. So obviously it needs to create, the membranes, the shells that it lives inside. It needs to create multiple copies of its DNA. It needs energy. And so it interacts with multiple genes inside us to be able to fulfill and perform these functions. And so these genes have been on the human side have been identified previously. And so what we decided to do is to look at the hypothesis was if the virus have existed long in the past in certain form, and it's obviously an ancestral form to the current virus because it keeps evolving through time, and it has used the same molecular machinery, which we have evidence for that different coronaviruses tend to use the same machinery. So that bit in its genome is a bit conserved across multiple coronaviruses. And then if it infected enough people back in the past, in the absence of medication, it's going to leave a massive signature of adaptation and on those particular genes. And so we scanned for signatures of adaptation on these genes around the world. As I said, 2,500 DNA from 2,500 individual from 26 different groups around the world. And we found evidence for that adaptation only in East Asia.
I see.
And,
yes,
yeah.
sir, and yeah, continue.
No, continue, please.
Well, I'm just curious because recently we've pretty much uncovered that coronaviruses has has evolved to a different strain. Can you tell us a little bit on how it evolved to that particular, like the strain? I'm curious to know how, when it jumped passes to humans, how did that, how did the coronavirus started to evolve in that strain to the point where it's becoming transmissible to other human in a faster rate?
Well, our research really doesn't focus on jumping viruses and also the fast mutation of viruses, like how coronavirus mutated from a year and a half or 2 years ago up until now. What we really focused on is the slower reaction and response to the presence of coronaviruses in a certain environment. But your question is very good, in that in a short period of time, we are unable to adapt as fast as the virus, because adaptation needs novel mutation, needs that the mutation spread through the population, and that takes several generations. And the reason why the virus is dangerous, because it mutates so much faster. Its generation time is probably in days, whereas our generation times are in decades. And so the virus will mutate thousands of times before we are able to adapt to it. And that is really the danger, is the mismatch between the speed with which a virus accumulates mutation and try to evade the detection and or defenses, with whatever those might be. They might be natural, which means the natural defenses that our immune system has, or unnatural defenses. Those could be like acquired through vaccines or medication. There also might be unnatural defenses as like masks and things like that. And so there's that continuous arms race between the virus and us, where we try to improve our defenses in many different ways, and then the virus tries to evade those in many different ways as well.
Yeah. And Yassine, are you hoping, and I guess you sort of alluded to this, but are you hoping that what you guys have discovered or what you guys have found might inform how, I guess, we handle the current situation, or might handle future pandemics? Well, what are your insights there?
So our findings, and in our discussion, what we try to highlight is that pandemics like these are not new. They have occurred. They've occurred far less frequently in the past, and their frequency increases basically linearly with the size of human communities. So the higher or the larger the human communities are, the more likely we're going to be getting pandemics. And in a world where we are 7 billion or over 7 billion now and growing still, the risk of pandemics is not going down. It's only going up. And the secondary sort of information or conclusion that you can extract out of our research is that viruses under certain conditions and of certain profiles can still spread in very small population. So we're talking this epidemic that we detected started roughly about 20,000 years ago, more or less. Human populations were very small back then compared to what we have now. Nowadays we have cities of 20, 30 million people. Back in the past, we were talking about human communities, probably if they get big, they probably around 100 people. And so even under those circumstances, you can still sustain a viral presence. And that's also in parallel have been demonstrated in Africa through the latest sort of Ebola epidemics, etc. That's a virus that have been maintained in communities that are fairly small. And you can only imagine if it spreads to, a city like London or something like that, that would be catastrophic, absolutely catastrophic. And the third and the last sort of conclusion, which is the most exciting to me, is that through an evolutionary lens, when we study these viruses back in the past, and they're dynamic with humans and other organisms as well, we can understand the biological functions in the host that actually interacts very closely with the viruses. And those are, and when we understand and characterize very, very well the biological processes involved in the response to a certain virus, that helps us design more efficient treatments and helps us design better vaccines. And so, and it can also help us in efforts for drug repurposing. Our research came a little bit late, admittedly, for different reasons, but just through this evolutionary study that looked at human genomes from around the world, and these are individuals that have not been, this DNA have been collected prior to the coronavirus epidemic. So we did, that wasn't a factor in the collection of that DNA. Even with that type of base level type of genetic information, we have been able to actually discover drug candidates that target the genes that have been adapted to an epidemic back in the past, that are actually drugs that are being used currently to treat the current pandemic. And so if we did this research prior to the COVID-19 pandemic, we could have given clinicians and drug companies a smaller list of candidate drugs that are likely to be more efficient. So instead of them spending 2 months trialing, I don't know, 200 or 300 different drugs, could have given them a small list of a couple of the dozen that they can try. And yeah, and in fact, about 5 out of the 12 or 14 that we found are actually being used to treat extreme cases of COVID-19. And so there is a lot of merit to these studies besides the cool story.
And it's amazing what you're saying, because it really opens your mind up in terms of how many different ways we can be like helping each other and trying to tackle, I guess, this evolving situation that is COVID-19.
Absolutely.
Whether it be frontline workers or, like research being conducted in the labs in various fields of the sciences.
Yeah, it's a concerted effort.
Switching topics from Corona for a little bit, what's the single most amazing fact that you've learned from studying ancient DNA that someone who maybe hasn't studied genetics or molecular biology would be able to appreciate?
There are several, but to me, personally, is we tend to think about human groups as these stagnant, independent units. You got Africans here, and you got sub-Saharan Africans here, and Northern Africans over there, and then Middle East, and sort of Europe and East Asia, and all of that. But as opposed to this classic perception, in the last 60, 70,000 years since humans left Africa, in that sort of initial migration, the amount of movement and mixing and that have occurred is absolutely staggering. And we wouldn't have learned to what extent if it wasn't for ancient DNA. So just to illustrate some of the craziness of the situation, you got a small group of humans left Africa at about 65,000 years ago. And in the Near East, sort of that Fertile Crescent area, which is what is Jordan, Israel, Palestine, that region nowadays, part of Egypt, they have met around there, an extent and basically an extinct cousin of ours, Neanderthals, who were occupying that area in Europe. they mixed with them. And then from there, you have groups that have split. Some of them stayed in sort of that Near East Arabian Peninsula area. Some have separated and went on to colonize South Asia, East Asia, and island Southeast Asia, and Papua and Australia. And then you have other groups that have migrated to go and colonize Europe. And I'm giving you just the simple story here. Then the group from that Central Europe area, that occupied that Central Europe area, subsequently migrated to certain parts of Iran and the Middle East again. And then you have groups that in Turkey have migrated few thousand years later back to Europe. And so everybody after that migration in Europe is a mix of that indigenous European group plus that Turkish sort of ancestry. And then a few thousand years later, you have the people that were living in the steppe, the Russian steppe nowadays, and sort of that Eurasian bit where you have Kazakhstan and those countries over there, migrated back to Europe. And so everybody in Europe by that stage became a three-way mix between the original migrants into Europe, the Turkish people were from the Turkish Anatolian ancestry, and then that steppe ancestry, plus that 2% Neanderthal they have in them. And then you have several migrations back and forth from there back to Asia, and then from Asia back to Europe, and then few migrations from the Near East up to Europe, and then backwards, and then few pulses from North Africa into Europe, and few have, made their way from sub-Saharan Africa to the Iberian Peninsula. So like that, if you will, between quotes, that genetic ancestry just doesn't exist. We're all related one way or another, and in a much more recent history than we might think. And sort of in a grand scheme of things, it gives you that staggering level of movement and interaction and trade and cultural exchanges as well that occurred with that. But it also, it's a message that should unite more than divide, and should tell us also about how rich our background and our ancestry really is.
So I guess the punchline, Yassine, what you're saying is it's just one human race.
There is no race. It's just we're humans.
Yeah.
Yeah. I'm arguing even that our extinct cousins like Neanderthals and Denisovans and maybe some others that we haven't discovered yet, we're just humans as well.
That's right.
Yeah. Thanks for your time.
No,
Appreciate
Thank you for your time, Yassine.
Thank you very much.